Okay, in geometry, for this lesson, we're going to introduce actually the final lesson in Chapter 4, and it's Lesson 4.7, and the topic is called Medians, Altitudes, and Perpendicular Bisectors. Now, this is really a lesson where you do have some definitions, and you'll want to make sure that you write these down carefully in your notes. The first definition is what a median is. Now, a median, and let me back up a little bit. It's hard to start with, keep a median and altitude separated because they are so similar, but there's one main thing that makes the two different, and that's why you got to be careful with your notes. A median is a segment from a vertex. Now, remember what a vertex is. A vertex is where two sides of a triangle meet, so it's kind of like the corner. So a segment from a vertex, a median is a segment from a vertex to the midpoint of the opposite side. So if I label this triangle, I'll label it triangle ABC. And let's say that I want to draw the median from vertex B. And I'm going to use a line here to do that. If I'm going to do this correctly, I want to hit, if I'm drawing it from vertex B, I want to hit the opposite side right at the midpoint. So I'll say this is the midpoint right there. All right, so now I'm going to draw a segment from vertex B to the midpoint of the opposite side. So that would be a median for this triangle from vertex B. Now let's say that I wanted to go from vertex C. So I want to hit the opposite side from vertex C, so the opposite side would be AB, and I'm just going to put a dot kind of where it looks like the midpoint would be. So I would draw this segment from vertex C to the midpoint of the opposite side. So in blue is the median from vertex C. Now how about from vertex A? I'll put this in a different color. So vertex A, I want to hit the opposite side, or side BC, at its midpoint. So it would look something like this. So a median is a segment from a vertex to the midpoint of the opposite side. So it hits the midpoint of the opposite side. All right, let's write down the definition for an altitude. Now an altitude is the perpendicular segment from a vertex to the line to the line containing the opposite side. So here's the difference between altitude and median. So I'm going to label this DEF. Now, let's talk about vertex D. Now, if I want to draw the altitude, now an altitude it doesn't have to hit the midpoint of the opposite side. What it has to do is it's got to be perpendicular to that opposite side. And this is just a sketch, but if I were to do this here, I want to make sure that I draw it such that it's kind of hitting it perpendicular. And that's probably not the best example, but you kind of know what I mean. So in other words, it's a segment from a vertex, and it's going to hit the opposite side such that it's forming right angles. So it's perpendicular. It doesn't have to hit the midpoint. Let me give you one more example. How about from vertex F? So if I'm going to draw, let's see, I want to draw a segment from vertex F such that it's perpendicular, and here I can, so maybe something like that, such that it's perpendicular to the opposite side. That is an altitude. Now, could I have a situation where a segment from a vertex is both a median, meaning it hits the midpoint and it's perpendicular to the opposite side? Sure, you could have that case. Now, in this section, we do go into a little bit more detail with altitudes, and you'll want to make sure you have this in your notes. Now, here on this screen, I have this labeled as altitudes in an acute triangle. Now, the altitudes in an acute triangle are all going to be inside the triangle. So in other words, I got to make sure my altitude is hitting the opposite side such that it's perpendicular. So that might be an altitude from vertex B. From vertex C, it might look like this. Just make sure it's perpendicular to the opposite side. And just to emphasize that, I'm going to put my right angle symbols. And then for vertex A, it's going to hit the opposite side such that it forms right angles. All right? So notice that these three altitudes are all inside the triangle. There's nothing outside the triangle. Now, is that the case for a right triangle? Well, let's see. For a right triangle, let's draw our altitude from vertex E. Now, from vertex E, it's kind of easy. So it's going to hit that opposite side such that it's perpendicular. So I'm just going to iron this here. So maybe something like that. Now, what's going to happen if I go from vertex D? Well, from vertex D, it's got to hit the opposite side. Well, you know what's going to happen? If it's going to be perpendicular to the opposite side, what do you notice about the altitude drawn from vertex D? It's actually the side of the triangle, isn't it? So in this case, it actually is one of the sides of the triangle. How about from vertex F? So in vertex F, I want to draw a line, a segment from vertex F, such that it's perpendicular to the opposite side. So notice here, from vertex F, it's actually a side of the right triangle. So in a right triangle, one of the altitudes is inside the triangle. The other two altitudes are actually the sides of the triangle. So again, make sure you're taking careful notes on this. So in an acute triangle, all the altitudes are inside. In a right triangle, one of them's inside, the other two are actually sides of the triangle. Now there's one more type of triangle that we need to talk about, and that's an obtuse triangle. So let's start with vertex Y. So I'm going to draw an altitude such that it's hitting the opposite side so that meets the form right angle. Now that altitude is inside it, isn't it? Now what's going to happen if I want to draw an altitude from X? Well, this is where it becomes a little different. So I'm going to kind of extend this side out. So X then is going to, the altitude from X is going to look like this such that it hits that extended line or extended side so that it's perpendicular. So what is the altitude from X going to be, inside the triangle or outside the triangle? Well, it's actually outside the triangle. Now how about if I wanted to draw the altitude from Z? Well, I need to extend, let's see, from Z, I need to extend this out, something like this, and then extend, so it would look something like this. And again, it's outside the triangle. So the main thing I want you to see here is for an obtuse triangle, two of the altitudes are outside, one of them are inside. And that might be the best way to do your notes, is just to write that down. Obtuse triangle, one altitude is inside, two of them are outside. For a right triangle, one of the altitudes is inside, two of them are actually the sides of the triangle. And for an acute triangle, all three altitudes are inside. Okay, another definition and final definition is what's called a perpendicular bisector. Now notice I have a line drawn. Now a perpendicular bisector is simply a segment or a line such that it's going to cross the midpoint. Let's say this is the middle of that line. It's going to cross the midpoint and it's perpendicular at that midpoint. So the blue line is a perpendicular bisector of the red line because it hits it at its midpoint and it's perpendicular to it. Perpendicular bisector. A couple theorems. Theorem 4.5. If a point lies on the perpendicular bisector of a segment. So the first thing I'm going to do is I'm going to draw the perpendicular bisector of this segment. So let's say that this is the midpoint right there. I'm going to draw the perpendicular bisector to it. So it's going to cross it at a right angle. And I'm going to move that over a little bit. Okay, so let's say that the blue line is the perpendicular bisector of it. Now if a point lies on the perpendicular bisector, so let's say that we have a point on the perpendicular bisector, then the point is equal distant from the endpoints of the segment. So notice what this is saying, that this point is equal distant from the endpoints. So in other words, this distance is the same thing as this distance. Or say that I have the point is right there. Well, from the endpoints, this distance is the same as this distance. And that's all it's saying. I can pick any place on the perpendicular bisector, and that point is going to be equal distant from the endpoints of the segment. Theorem 4.6, if a point is equal distant from the endpoints of a segment, so now I've got maybe something that looks like this. Okay, we don't know if it's perpendicular or if it's hitting the midpoint of that black segment, but say we do have a point, and we do know, I'll make these lines a little straighter, say I do know that that point is equal distant from the endpoints. So I do know that those lengths right there are equal distance. Well, you know what? If that happens, then that blue segment has to be perpendicular to the black segment, and it has to hit that black segment at its midpoint. So it's the converse of Theorem 4.5. All right, Theorem 4.7, two more. If a point lies on the bisector of an angle. Now, what's a bisector of an angle? Well, the bisector of an angle is simply a segment or a ray that cuts an angle into two equal parts. So say that this ray right there cuts this angle into two equal parts. So we know that this part equals this part. So if a point lies on the bisector of the angle, so let's say we got a point right there. So that's the angle bisector. Then the point is equal distant from the sides of the angle. So what's this saying? Well, let's see. It's equal distant from the sides of the angle. So here and here. Those are going to be the same. All right? And notice my bisector probably isn't exactly in the middle, and that's why those two segments don't look the same. But you kind of get the idea. So no matter where I put that point, and you draw the line from the sides of it, okay, those are going to be the same. All right, last theorem, Theorem 4.8. If a point is equal distant from the sides of an angle. Now it's kind of like with the perpendicular bisector. So I'm going to draw this. And say that I know that the point, say that I know that this is the same distance as that. Well, the only way that they can be the same distance is if this ray does bisect the angle. So if there's a point on the bisector, or on the ray, and it is equal distant, so say we have this, say this, and those are the same distant, you know what? This has to be an angle bisector. So in other words, it cuts the whole big angle into two equal parts. Okay, now, that's, again, a lot of definitions, but make sure that you have those down carefully in your notes. And again, this topic was medians, altitudes, and perpendicular bisectors.